nearly as much time on that as we did the first derivative. So we are at, we just finished, we went through example 5 yesterday. So we're at the box in the middle of the second page. So your second derivative. All right. If we think about our graph, we know the first derivative tells us if we are increasing or decreasing, right? So if I'm looking at this one, my first derivative, what would be true about the first derivative? Yeah, the graph is increasing, so the first derivative would always be positive, right? Your first derivative is just looking at those tangent lines, and every one of those has a positive slope. If we then graphed that first derivative, so here is like the derivative of that, what we see is this one would also have positive tangent lines. So the second derivative is positive as well. It is showing us concavity, or the curvature of the graph. This original graph is what we call concave up. It's curving upward. Concave down is like this, where it's curving downward. So like upward, it's like a bowl. It would hold something. Downward, it's turned upside down. It's going to fall out. So if our second derivative is positive, that's going to be concave up. If it's negative, that will be concave down. So this is our concavity test. So that's where you need to fill in the blanks there. If the second derivative is positive, then the graph is concave up. If the second derivative is negative, it is concave down. Let's look at a problem. So this figure shows a population of honeybees. How does the rate of the population increase change over time? When is it the highest? When is the graph concave up or concave down? So this graph is just showing population. Okay. That means, at time 0 we had no honeybees, and, by time after 18 weeks we're up to about 70,000 honeybees here. So my first question is, how does the rate increase over time? Not the number of bees. Obviously the number of bees increase, but how does this rate change? The rate is talking about the derivative. Derivative is the slope of the tangent line. So we're talking about basically the steeper the tangent line, the faster the rate. So if you're looking at the beginning, okay, these are increasing, but is it very quickly? No, because those tangent lines are fairly flat. But then what happens after, like when you get to about 9 weeks? What's happening? It's getting steeper. That means our population is growing really, really fast there. And then what's happening towards the end? It's slowing down. Okay, so the rate was low in the beginning. Increased. Then slowed down again. We were always increasing our number of bees. We never dropped, but we can see at the beginning we weren't adding bees very quickly. Then all of a sudden we had a big population spurt, we added bees really, really fast, and now our population growth is kind of leveling off again. Okay, then the next question was, when is the rate the highest? So we're really just looking the fastest growth. When does that happen? Kind of starting at 9 and maybe ending at 12, you think? then I want to know when it is concave up and concave down. From now on, I will use CU for concave up and CD for concave down. Okay, concave up means our graph is turned upward, kind of like an upward facing parabola. So if I'm looking at this first part, is that curved up or curved down? Yeah, it starts out curved up. You know, if I finished the other side, we would have an upward parabola. So it's concave up from 0 until about 12-ish. But then after 12, what's happening? It's curved downward. If you finish that, you would get an upside down parabola. So it's concave down from 12 to whenever this thing stops. Any questions there? So 12 is actually a special point here. We know critical points are where our first derivative changes from positive to negative. When your second derivative changes from positive to negative, that is called an inflection point. So I have that definition at the bottom of your page. I just kind of summarized it in my own words, not the words from your book. So your inflection point is just where the concavity changes. So if we think about this, we can make some connections between our different types of graphs. So I have on your page what's called the second derivative test, and I want to talk about that. So we have this box. We're going to fill in the blanks here. Okay, if we have a continuous graph, so the first one I said if the first derivative is 0. If my derivative is 0, what's going on at that point? Horizontal and tangent line. So that means it's either a maximum or a minimum, right? And the second derivative is positive. If the second derivative is positive, what does that tell me about my graph? Concave up. Okay. If your graph is curved upward, is that point a maximum or a minimum? Okay. If you're going to be curving upward, it's got to look like this. So that means C is a local minimum. Second thing, if the first derivative is 0, which again, if we have 0 for the first derivative, that tells us it's either a max or a min. And the second derivative is less than 0. If the second derivative is less than 0, that means it is concave down. So if you're going to be curved downward, then it is a max, local max. I don't use this a whole lot. First of all, I think it's something we can reason through. It's not necessarily something you need to go home and sit and study and try to memorize, because we can kind of reason through it. The second reason the second derivative test isn't always all that great is because if the second derivative is also 0, it doesn't tell us anything. So we are going to use some other tools to kind of make all these connections and figure out if we have maximums or minimums. We know we can use the first derivative test to tell if it's a maximum or minimum if we look at the increasing, decreasing. So I tend to rely on that, but this is still useful to mention. So I want to throw a challenging problem at us. I want to try to draw a graph that meets a bunch of different criteria. And I do have a typo here. the second criteria, it should say the second derivative is greater than 0 on that interval. Okay, so we have to draw a graph that meets all of these conditions, and there are a bunch of them. So we have to figure out what each of these things is telling us. So the first condition says the first derivative is greater than 0. If my first derivative is greater than 0, what does that tell me my original graph is doing? Increasing. So that means it's increasing from negative infinity to 1. And the second derivative is less than 0 on 1, so that would mean decreasing. So that means my graph was increasing and then it switched to decreasing. And that happens at 1. So if you go from increasing to decreasing, what happens at 1? You would have a local max at 1. Okay. Second thing says the second derivative is greater than 0. Greater than 0 for the second derivative means it is first derivative positive is increasing. Second derivative positive means it's concave up from negative infinity to negative 2 and from 2 to infinity. Second derivative is less than 0, so concave down between negative 2 and 2. Right, so that means we have inflection points at negative 2 and positive 2. All right, third condition. The limit as our graph goes to negative infinity is negative 2. So that's like a horizontal asymptote. When we're going forever in the negative direction, my graph is approaching negative 2. The limit as x approaches infinity of our function is 0. So when we go forever in the positive direction, we're just approaching 0. So we have a couple different horizontal asymptotes here. So now I have to put all this together to make a graph. So I know my graph has to be increasing until we get to 1. Okay, so 1 is a local max. I didn't tell you where, so I'm just going to put a point. So my graph has to be rising until we get to there. Now, I know that it is concave up until I get to negative 2. So again, I don't know where. I know my graph is approaching this asymptote. Inflection points I typically mark with little x's. So my graph has to be curved upward but approaching this asymptote. So something like this. It's curved upward. This is an inflection point. So now my concavity changes and we're curved downward. We have to hit our maximum here. So inflection points is a lot of times just a very subtle change from concave up to concave down, not something drastic. We are still concave down until we get to positive 2. So somewhere at positive 2, I'm going to put a little x. So I'm still curved downward. But I know my graph has to keep decreasing. We have to get close to this asymptote, and now it's going to switch and curve upward. Okay. So that is an example of a graph that would meet all these requirements. It is challenging to draw these graphs when I throw so many different conditions at you. So I break it into pieces. Make sure you know what each condition means. Okay, take the time to write it out like we did. You know, if this means increasing, this means concave up. Look at those maxes and mins. And when you get to the end, it's always a good idea to read back through all those criteria and make sure your graph matches everything. Questions on that? I want to look an example of testing a graph for concavity. So I want to look at the next one. So yesterday we did maxes and mins, and we found increasing and decreasing. And to do that, we had to do the first derivative and find our critical points. If I want to find concavity, I need inflection points. So we have to do the second derivative. An inflection point is really like a critical point except in the second derivative. So we're going to do the second derivative and figure out anywhere it's equal to 0 or undefined. So my first derivative would be 3x squared minus 6x. If I wanted increasing or decreasing, you would set that equal to 0, but I didn't ask for it, so we go ahead and do the second derivative, which would give us 6x minus 6. Is this ever undefined? No. So we just need to figure out what makes it equal 0. And we get 1. So 1 is my inflection point. I use IP, inflection point. That is where my concavity can change. So yesterday, if we were figuring out increasing or decreasing, we did a sine line. And we plugged our points into the first derivative. Concavity is based off the second derivative. So I am going to have to plug my points into the second derivative here and see if it's positive or negative. So a point smaller than 1 and bigger than 1. So if I put in a 0, we get 0 minus 6, which is negative. If we put in a 2, we get 12 minus 6, which is positive. So where is this graph concave up? From 1 to infinity. Where is it concave down? Negative infinity to 1. So you're finding out where the second derivative is positive or negative. Questions there? So what we are leading up to is taking all of this information and drawing graphs. So I'm going to do one of those and then I'm done for today. So when I ask you to do these, there are going to be a lot of pieces to it. So I'm going to ask you to find everything. Critical points, maxes and mins, increasing, decreasing, inflection points, concavity, and then put it all together on a graph. So let's kind of start this problem. We're going to begin with our maxes and mins, or in our increasing, decreasing. So we have to find the critical points. So we do our first derivative. So that would be 4x cubed minus 12x squared. Then how do we get the critical points? What would you do to that?
Take minus 4x squared.
Which is x minus 3. So what are the critical points? Where is that equal to 0? Okay, so we have our critical points. Then I would ask you to find increasing, decreasing, and maxes and mins. So we did a sine line yesterday for that. Put our 0 and our 3. Smaller than 0, in between, bigger, we are plugging these into the first derivative. So I'm plugging them back in here. It might be easier for plugging in purposes to go to the factored form. You can do either one, and you'll get the same thing. And all we care about is if it's positive or negative. So 4 times -1 squared is positive. -1 minus 3 is negative. Positive times a negative is. If I put in a 1, we get 4 times -2, so that would be negative. If we put in 4, 4 squared is positive, 4 minus 3 is positive, so that is positive. All right, so where is this graph increasing? Where is it decreasing? Everywhere it's negative. So those of you that were gone yesterday, this was like half your problems were telling me where it's increasing or decreasing. The other half were telling me the maxes or mins. So from this, does anything happen at 0 if you were decreasing and you continue decreasing? No. At 3, we were decreasing and then we switched to increasing. So what happened at 3? Local max or local min? We are going to be drawing graphs, so we need the full ordered pair for that. So to get the y value, where do I need to plug the 3 in? The original. So 3 to the 4th is 81 minus 27. -27? So this one has no max. Okay. So that's all the stuff from yesterday. Today we learned how to find concavity and inflection points. So for that we need the second derivative. So that would be 12x squared minus 24x. And to find the inflection points, we need to figure out when that equals 0. So we can take out a 12x, that leaves us with x minus 2. So what are my inflection points? So to figure out the concavity, we need the sine line. All right, so smaller than 0, in between 0 and 2, bigger than 2. So if we plug in a -1, again, you just have to plug it into the second derivative. It'd probably be easiest if you do the factored version. So that would give us 12 times -1 is negative. -1 minus 2 is negative. Negative times negative is positive. If you put in a 1, you get a positive times a negative, which is negative. You put in a 3, positive times positive is positive. So everybody understand where I'm getting my positives and negatives? So this graph is concave up where?
Negative 0.
And to infinity. And concave down? 0 to 2. All right. Now I want to draw our very own graph without a graphing calculator. It will be beneficial to get ordered pairs for these inflection points so we can mark them on the graph. So again, we just plug those into the original to get that. So if you put in a 0, you get out 0. If you put in 2, 2 to the 4th is 16 minus 32, so negative 16. So we have some information to plot. We know we have a minimum at 3, negative 27. I certainly do not expect you to count by ones on that. I'm just going to count by tens on my y-axis. So 3, negative 27 will be out here. Our inflection points, I want you to mark those with X's. So we have an inflection point at 0, 0, and at 2, negative 16. So now, we know our graph is decreasing to start with. Until we get to my minimum, it's decreasing. It is concave up until you get to your first inflection point. So decreasing, but curved upward. I have to keep decreasing until I get down here. But what's happening between 0 and 2?
It's got a dash turn.
Okay, so, oops, that's not very clear. So it's somehow turning downwards, so that's slightly exaggerated, but shows the concavity there. And then what happens after 2?
Up.
It's curved upwards the rest of the time. We're still decreasing. We hit our minimum, and then it increases, but it's still curved upward. So that is our final graph. So we just completely graphed a polynomial by hand. Questions?